Yeah, I guess let's kick it off. It looks like we're right on time here. So yeah, hi folks. I'm Leo, founder over at Graphistry, and I'm going to be talking about going for 100 gigabytes per second for GPU log analytics at Graphistry. And so today you're actually getting a twofer. So one, we'll be talking exactly about that, just some of our recent hijinks trying to achieve that, and hopefully ways you can too. And then we actually try to build not just like, one-off notebooks where if things crash, nobody cares. We actually try to build software that's like always on, reliable, and imagine you don't want your dashboard to like, flop out on you. So I'm talking about some of the things that as we were building the software, we wish somebody had told us. And so hopefully I'll save you some pain. And I would be remiss to not share some credit here. Graphistry actually helped start what is now called Nvidia Rapids. That's spun out of a GPU data frame prototype at our team, actually, like when I was back at Accenture. And a lot of the stuff today is actually, we'll be talking about GPU direct storage, where we're getting a bunch of help from the NVIDIA's GPU direct team, the Rapids team, and then I'll talk a little bit about something called Pavilion for the storage side. So really briefly about us, because this is really about technology, not us. Graphistry is a startup you've probably not heard of, but we do cool things, as you're probably getting. So we helped start, we wrote the web tier of Apache Arrow. We work with enterprises, federal agencies, cloud companies. Gartner recently gave us a cool vendor award. And what we basically look at is if you have a lot of event data or log data, can you see the correlations in it? Can you see, we'll do like graph analytics, GPU acceleration, so you can actually find the patterns and investigate through them. So you'll see a little bit about that. So the first thing the first part of the talk, I want to just kind of do a quick demo to get you a feel for the types of experiences that we've been working to enable. And this is, I'm going to start with a case study. The data for this one is actually open. It came from Splunk's boss of the SOC. The SOC is your Security Operation Control Center or Command Center. And the data set that we're looking at here should feel kind of like a lot of the logs that a lot of teams are probably working with today. So we're going to be looking at a 70 gigabyte dump of Windows security logs. And you can see one event on the left here. It's pretty nasty. So it was kind of structured. So one event is actually pretty wide and has all this like weirdly structured data in it. Different Windows events are structured differently, depends, different OS versions. And that for the boss of the SOC challenge, that's just one of the data sets. There are about 20 data sets. And then the question is, hey, I think we were hacked. What happened? And then you have to kind of bounce across all of them. So it's pretty tough. And again, if let's say you're not doing security, but you're doing fraud, or you're doing like network IT and you're looking at an outage, or maybe you're on the commercial side of the house and you want to do like a customer 360, or you want to do patient journey. Basically, the world runs on logs nowadays, and this is all kind of feels pretty similar. So demo I want to show, let's actually go to we'll kind of do a live version or a pre-recorded version. So what we're looking at here is something called a little dashboard we set up to work on the GPU accelerated versions of all this stuff. So it's using Streamlit. So you might know Plotly or Streamlit. These are basically easy Python dashboarding tools. And then underneath, where we're using Graphistry and Rapids and things like that. On the left, we have these little interactive sliders. So the question is, can we work on the entire data set, or only can work on a time range interval? And so how much data can we do while staying interactive? And then we can play with things like how many GPUs we're running on. So in this case, I think we were running on a box where we can go from anywhere from 1 to 8 GPUs. And as we kind of do the search, the dashboard will kind of update which events we're filtering down to. So what I'm going to show on the right is a couple things. So when we did one search, let's say we filtered down to some of those, like in this case where I think we're looking at unusual logins. And so we're looking at top 50 logins for that interval. Just being able to do a search over 70 gigabytes or like 7 terabytes of data and just make that interactive, that's already, and make it so you don't have to code, that's already a big deal for just like any analyst who wants to think about, finding the outage or finding the incident versus writing Python. So that's important. But the other part is, even if we can get the data in there, I don't necessarily want to look at, 50 login events or 10,000 login events. That doesn't necessarily make any sense. And so one of the things actually where Graphistry starts coming in is we can actually take those events and then make a GPU accelerated visualization out of them. So you can go to more of a, not just a dashboarding session, but a visual session. And so what I wanted to show here, I'll kind of speed it up a bit, is we can take those same events and then put them on screen where we just extract any entity and make it visual and interactive. So we're seeing the MAC addresses and account names and things like that. And actually what I want to highlight on the bottom right here is, like, for example, we can see histograms of like priority numbers or whatever. And so instead of having to manually filter, we can actually use the UI to do those things. So that's the kind of experience that we're interested in doing. So if you have that, 70 gigabyte log dump from AWS or Splunk, can we actually see it and interactively work with it? So, and not only can we compute on it, can we actually do it like in a visually sane way? And so one of the core pieces here is the data wrangling and data analytics part, and we want to make that as scalable and interactive as possible. So as kind of a warm up, I want to talk about a bit from the path going from pandas to dask-cudf. That's been a big theme of Dask Summit this year. So I'll be a little more brief on that. So let's jump in here. And actually, even before that, the question is like, is this even practical from like, if you're going to propose this to your like CTO or whatever, like, does this even make sense? And something I do every year, I haven't actually updated it yet for 2021. So I think last time I updated it was at the beginning of last year, is I take a look at are GPUs even affordable for kind of regular usage outside of this like very occasional deep learning training, which is important, but generally a tiny piece of what most of the organization does. And so the question, question if we want to swap all of our CPU workloads for GPUs is like, is it faster? Is it more affordable? Things like that. And so I look at a couple things, like how far does our dollar get us in terms of just floating point operations per second. And when we look at like the AWS EC2 costs over the last 10 or so years, it's been about a 30x over, and you can see it's actually pretty nice. It's actually log scale, so it's kind of following this nice exponential. It's dropped about 30 times. And so at some point, and I think it's already passed, it's now more cost efficient in terms of the amount of compute you get than something like CPU. And at the same time, the amount of on GPU memory for doing more and more realistic and kind of non-toy use cases has also been dropping. So over the last 10 years, we've also seen that 20, 30x increase in for $1 how much GPU RAM you get. And I think that those are two good measures. I think actually the previous speaker was talking about AWS's T4 instances. So those are particularly price competitive for if you just want to have sustained use. So that's so it's already like a thing that you could just go to the cloud and get, and it makes sense. Now now that like we're allowed to use it, I'm going to kind of go over a bit about how to use it and make that kind of easy. So baseline here, a lot of data wrangling nowadays is in pandas. So I wrote a very basic one-liner here. So you read some Parquet file or a CSV file, we pull out some unstructured text column, and then we do something like run a regex on it. In this case, we maybe want to look at the Windows event code and then make sure that instead of have it as a string, we turn it into an int. And so pandas and CP libraries are kind of nice for that. Maybe use SQL or Spark if you're working with bigger stuff, maybe Dask. The kind of a thing with pandas in particular is it only runs on one CPU and one thread of that CPU, and it does not use any of the SIMDs, so it's really bound. So if we push in something like a 50 megabyte file, that's going to have issues. That's just purely based on the single threaded CPU speed. And so what's kind of cool is before we even have to go to think about like distributed computing with Dask or anything like that, I would actually nowadays, I jump to something called cudf, where I could really take that exact same pandas code. I don't have to think about lazy semantics or any funny things like that. I really just do that same pandas API. And then in this case, we have about 100x speed up. So no need to get a bigger machine or whatever, just get a machine with a GPU on it. And it's that the only real caveat for this is for what works here is that you're actually not using the full pandas API. You're using the vector subset. So here you see that I'm always working on the column at the column label or the table level. If you're a PL person, you might call this point free. In practice, that just means you can't really do like a lambda over any individual value. Like you have to kind of keep writing at this columnar level like I did here. So, but as long as you stick to that pandas subset, this is pretty ridiculously fast. And as you saw, it'll give you more bang for your buck than the CPU approaches. The problem is, never a free lunch is, let's say we're working over a couple of columns and those columns are, let's say, more than 2 gigabytes. then all of a sudden, even though you might have something like a 10 or 16 gigabyte GPU in terms of the RAM, and that sounds like that should fit, the problem is you have a working set. So the kind of the runtime memory to work on that raw data column might exceed how much the GPU has. And so even if it feels like your data set fits in the GPU, it might not actually have room to work. And so all of a sudden now we think like, oh, do I need more GPUs? Do I need to start batching up the thing into working chunks? And that's actually where dask-cudf really, which is a kind of the cudf equivalent for Dask, and actually it's just an extension to it. It's almost like a wrapper on it with some extras. That's where it comes in. We get to use the same Dask API. And so where you might work, it's kind of the same code as before, but now instead of working on one data frame, we now work on data frame partitions. You can use all your regular Dask codes for it, but like if you're new to Dask, that's how you think about it. And so instead of one 100 gigabyte data frame, you could think it'll just automatically chop it up into 10 gigabyte data frames for you, things like that. And so this is pretty cool. As a few things here, I think the most one I want to point out here is, as with cudf, we're seeing these ridiculous speedups. So like on an 8 GPU, I saw about a 400x speed up instead of just the 100x. And then with a bit more code, if you're aware of a bit more of the tricky stuff, we can actually bump that up closer to 600 or 800x. And that's pretty awesome. We still actually don't have to worry about distributed computing and like clusters and whatever. This is all just running on one machine. So that's pretty amazing. And you can do terabytes of data, and it's not a problem. So, and if you want to learn more about that, go to the Dask websites, things like that. So what I want to chat about is actually, what does it mean to build software this way? So not a one-off notebook, but something that is always on. People go to the dashboard and it just works. So the first thing is just understanding Dask. This is a little introductory for, I think, a lot of the attendees today. So I'm not going to kind of go too deep here. But basically, the way to understand it is when we're doing Dask works just like pandas or other data frame systems, where we create a new data table based on old data tables. So it's kind of functional programming. And then underneath, what's going on is sometimes we want to dip into the fact that when it's actually partitioning each data frame into little sub data frames. And this gets useful for the other side of the data model, where you might want to manipulate two concepts. One is each of those data frame operations on one of those partitions, that's a kind of like a subtask. And as you see here, once you change it together, it becomes a graph. And then the other abstraction that you end up manipulating a bunch is the notion of workers. And so you might have one worker per CPU, or maybe one worker per GPU, things like that. And then each worker will be working on one partition or one subtask at a time. And they'll use something called work stealing to balance that out on the fly. Dask actually is a platform, so has a bunch more other stuff, but basically they're all phrased in terms of those concepts of clients functionally building out your task graph, and then the workers dynamically eating up chunks of that task graph for you. So with that said, this is all sorts of problems in practice do show up. So one of them that we see, we want software that doesn't crash for our users. And so one of the things we often see for crashes is actually Dask's approach to dynamic typing goes wrong pretty often. And what I mean by that is the way that Dask thinks about keeping type safety and keeping things ordered, when it's splitting up computations across partitions, it needs to make sure that when it puts the data frame back together, it all kind of each sub-column stitches together into one cohesive column of the same type. But then we have questions like maybe one of the partitions is all nulls, and when it tries to look at adding null to null, instead of guessing that it's getting int out, maybe it guesses it's getting a null out or something like that. And once we get into, let's say, floating point or int versus floating point, it gets confused pretty quick. Even if your code is right, Dask will be wrong. So you shouldn't feel bad, but you have to do work. And in practice, what we see is a couple of things. One is you have to be really explicit about, when you're doing parallel operations, about the metadata that the data frame schema you're expecting to get out. Sometimes, actually pretty often, we have to explicitly coerce the partitions to make sure they match that schema. And then we write lots of unit tests to actually enforce this. So this eats up a lot of time that you would not have spent in, say, pandas. Then more on the performance side related to that, a cool capability of Dask is that it's going to sort of optimize how each worker goes down the task graph, where basically, and this is going to be a little important later, instead of paging memory in and out, which is going to really kill your performance, is try to, as soon as a data frame comes in, it's going to try to reuse it for the next step of the next worker, or I mean on the same worker. So for example, the green thread might work on a task, and then it's going to kind of want to go on to reuse that for the next step rather than going on to one of the other ones from that initial partition set. So you see it's kind of going depth first here. So that's great for performance, but that's pretty confusing for things like debugging. And sometimes when you're doing certain optimization scenarios where you actually have too much parallelism, you just need to be aware of it. I'm not going to go deep on this one, but I do want to point out one of the things we end up doing, therefore, is when we want to do stuff like printf debugging and having nice traces, is we kind of take advantage where we kind of do two levels, where one is when we're in debug mode, we're trying to track these things down. As whenever we have these big, whenever we have a transform, we might actually force it in debug mode to compute it. And then when we're in trace mode, we'll actually go all the way to actually print it out. And so that way we can kind of see it. But then when we're actually doing real operations, we don't have to pay any of those costs. Related to that, likewise, nowadays, if you want observable software, you're probably going to do something kind of like requests, like request handlers. So imagine like an RPC call or like a web command. Dask internally has some cool tracing capabilities, but that's sort of at odds with how modern software works. And so for that, the way we do it is you can actually name your Dask clients, and you can kind of get, so we can put our request ID as part of the client session, and then we can add that to our tracing stack. We'd still love to go a bit further here by combining Dask with something like open tracing to really do how, end-to-end application monitoring. But I did want to point out that, the HPC world of Dask isn't starting to collide with the rest of the software world. And I think this might be one of those useful pieces. So that's all really about the CPU side. So let's say we want to write GPU software, not CPU software. So first thing to know about Dask is, and you pretty much are going to want to run separate workers for your CPU versus your GPU workers. You might be tempted to, for simplicity, not to, but you'll get, basically the problem is, let's say you have one GPU and 8 CPUs, which you might have, let's say for AWS T4 instance. You don't want to have your GPU workers being kind of working on a CPU task, and then when you actually have a GPU task, having no GPU available, because it's each worker kind of blocks on one task at a time. And so you really do want to run separate workers for those. And kind of the notion of a work unit is different. And so you really want to, you could use the same scheduler, but you want to make sure you do separate them. And a little bit for reference, I'll include code for how to actually use the fact that you're labeling one worker as able to do CPU code, while the other one is able to do GPU code. For a lot of this bigger than memory stuff, it is important to talk about the memory and the data you're pushing in, because that ends up being, that'll actually be a big focus of coming ahead. And so for storage, a few things. You don't really want to do CSVs or JSONs. They're pretty inefficient. They're slow to read. They're big and bulky. If you have less stuff and structured stuff, just everything works better. And so we do recommend doing Parquet or Orc. You're probably going to want to compress it, especially if you're dealing with these really big volumes. You should benchmark it. I've checked two things. One is, could you actually run uncompressed? Is that in your budget or is it not in your budget? And the same thing, this is not obvious, but you actually might run faster by saying uncompressed, because you don't have to pay for the compression or decompression time. So that really varies. I recommend checking it. But the main thing is, as soon as you have a chunk of file that you want to load in, like for one of your tasks, and so in Parquet, you can split up your logs or whatever in these chunks. I do recommend making sure it uncompresses into about 1 GB. I'll get into that in a second. And then if you are using compression, use something like a snappy codec. And the reason is, instead of using CPU compression and decompression, it'll actually send more data through in a compressed way. So it's like more gigabytes per second. And then instead of wasting CPU cycles on the compression and decompression, it'll actually take advantage of GPU acceleration and just do that right there. And so you'll actually also, if you are going for compression, just make sure you're using one of the codecs that support it. Now, let's say when that uncompressed chunk is a gigabyte, or let's say if it wasn't a gigabyte, you're going to have to on the fly cut it down to a gigabyte. And the basic reason is, let's say you have like a 12 gigabyte GPU. If you put in 12 gigabytes of data, of like a partition that's 12 gigabytes, you're going to have no extra space for your working set for for the extra data that your compute actually needs. And so different tasks will have different sizes of the ratio that you need to have of the raw data versus the working space. So you need to figure that out for your workload. Like thinking about like a 10x ratio, that's not bad. So we often kind of start there. So maybe a 200 megabyte snappy will decompress into about a gigabyte of uncompressed, and then that'll leave us another 10, 11 gigabytes for the actual working space. So that's often something we'll see on a lot of GPUs. So another thing that we see in practice here, and on that note of benchmarking, when we were looking at performance of cudf, we were kind of surprised by a lot of the performance overheads. And what we realized is that because cudf and dask-cudf try to follow the pandas and dask APIs, that's both a blessing because it's accessible and it's familiar, but it also ends up being really slow. And what I mean that is it kind of inherits the design bugs of those systems. So as a very concrete example, I really like using the operator assign, and we had this all over our code base, I don't know, like hundreds of times. And the thing is, if you actually look at how pandas and dask and cudf implement it, it desugars to something like this on the right. So if we're going to create a new column x equals 1 on our data frame, but make it a functional copy, it's actually going to do a deep copy of all that data. So if we had a 2 gigabyte data frame, we actually, that assign, instead of just creating a column and that's just a constant value and keeping it all symbolic, that's actually going to do a 2 gigabyte data copy. And then you're going to get your column with however it's dealing with the 1. So that's pretty terrible. And there's through the entire core library, like each operator is actually worth understanding, join, merge, all that. Like, are you actually hitting these gotchas? That might be good because maybe later you can get a 2x performance increase by just writing stuff in a fast way, but it's good to be aware of. And I'm gonna skip this one for now, just in interest of time. So hopefully you're getting a bit of a sense of what operational code, as you go from notebook code to production code, what that sort of feels like. So now I want to talk more about how do we go to bigger data sets. So when it doesn't all fit in GPU memory, like let's say you're doing log search or something. And before we talk about software, I want to actually focus on just what the hardware can do. As soon as the data is in GPU memory, things are ridiculous. So we're talking about teraflops of compute, terabytes per second of data moving between GPU RAM and between different GPUs. But the problem is, if let's say we're reading the logs off disk, like let's say SSD, an individual SSD might be able to have terabytes or whatever of storage, but you're only reading it at maybe half a terabyte or a few gigabytes half a gigabyte or a few gigabytes per second. And so if we want to write software that runs at 100 gigabytes per second, this doesn't really work. And you could buy more expensive and fancy storage cards, but we're not getting to that 100 gigabytes per second. We have to think a little differently. So kind of a naive, but actually pretty good in practice method is, why don't we just get a lot of smaller SSDs? And they could be wimpier, they could be beefier, but the important part is they chain together into controllers. The controllers in themselves might not actually be at our 100 gigabytes either, but if you have a few of those controllers put together, then as long as we're doing parallel reads, let's say a file striped between different, let's say our Parquet file, each part goes to a different SSD or to a different file system, however you map it, then in aggregate, we could get that. As long as we're doing that parallel read, in aggregate, we could get to those bigger gigabytes per second. So when I was referencing Pavilion, they're a good example of one of these modern storage companies that will actually sell you a storage array that's based on this stuff. And then as you have more storage, you could just, instead of having to buy a new computer, you can just slot in some new drives. So that's pretty cool. So now that we're actually getting data off our storage at a pretty fast clip, now we need to get it to the GPU itself. And we still have to think a bit more. And traditionally, and probably most of this talks today, they kind of assume that you're going to get your data from storage or from Ethernet. It's going to go into your CPU RAM and then maybe bounce through the CPU, through another PCI card to the GPU RAM, and then all the way to the GPU. So there's like a lot of stuff here happening. But a problem is, actually, I'm going to use a diagram to show this a bit better. If we're going to go from our storage on the bottom to our CPU and the CPU RAM, and then back to the GPU down here, that means, and again, we're trying to do these parallel reads if we have multiple storage. So we have, I guess, here 4 storage cards. If there's ever a bottleneck on the way, let's say one PCI card that both goes through, that means we're going to have to make sure that piece is rated for 100 gigabytes per second as well. And most PCI cards, like PCI 3, which most people have on, for example, the cloud, that's more like something I think it's like 16 or 32 gigabytes per second. And you're going to have that kind of problem all the way. You're going to have to make sure all the way up and all the way back down we're rated that way. So that's a problem. The cool thing is, like, this picture also kind of tells you sort of, well, why are we doing all of that? And there's an interesting technology called GPU, oops, it's up here, GPU Direct, which is actually a family of technologies. And the one for storage is about, hey, could we get data directly to the GPU from the storage tier? And they have the same thing for networking and other things. And I'm going to talk a little bit about what that looks like. So let's say we have our data frame and we actually, or a big Parquet file, and let's say one part lives on one storage controller and another part lives on another storage controller. So the first thing is we have to go from the storage controller through the PCI card to the GPU. And so let's say you do our read CSV or read Parquet. On its own, we could do maybe 16, 32 gigabytes per second that way, somewhere in that range. But then, and likewise, if we have actually another GPU, we can actually read that same data, and then it'll go the same way, and you can have a little bit of sharing. And we call this something called a NUMA node, where you have a couple of one or two GPUs sharing that same pathway. Now, the thing is, if we have a third or fourth GPU, we don't want to also go through that same pathway from the storage to the PCI card to that other GPU, because it's already saturated by those first two GPUs doing our reads. That other GPU really needs to go from the other storage card, the other PCI card, and then get to our GPU. So that's we need to be careful about doing those parallel reads. Importantly, we're not bouncing through the CPU, we're not bouncing through the CPU RAM, we're not bouncing through their PCI control buses or anything like that. So we really just want to keep it around here. And then for subsequent computations, we want to kind of keep the GPU, the compute within the GPU. And it's actually cheaper to go cross GPU once it's loaded in. So there are things called like NVLink, whatever that, I think nowadays like 2 terabytes per second, really fast. But the important thing from this picture was that when we do those reads, we really want to make sure that we're getting these dedicated paths. So we can saturate it without any of the other GPUs taking it from us. You could do that in code. I share that on the slide here. I'm not going to go over it, but the slides will be public. But basically, as long as you're aware of where your partitions are coming from, you can do it. I do want to note that setting up this kind of flow is tricky. And that's in a couple of ways. So the first thing is, the bad news is Rapids, which is sort of the dask-cudf part, only recently started integrating cufile, which sort of lets you doing that kind of skipping the CPU parts. And so even though it technically works now, we're only seeing speeds somewhere about, I think, 2 or 3 gigabytes per second for that. But the underlying CUDA libraries are much faster. And so I'm going to talk a little bit about that. So the first thing is you want to make sure that it works. So that's the GDS check. The second thing is you want to make sure at the OS and container level, so even before we get to Python, that you're actually, all your hardware is configured. And so the best way to do is actually try to do a read test. So you just write out some data. In this case, we're writing out data for having four readers. And then you're going to do a read check. And you can it should tell you how many gigabytes per second you're doing. And you already will start noticing gotchas. So in our case, for example, we were able to get to about, per PCI card, about 20, 25 gigabytes per second. But we had to bump up the number of CPU reader threads to, from 4 to I think about 20 or 30, something like that. And so you'll start getting a feel for what your hardware is able to do. And in turn, things can always go wrong. So you really do want to look at the performance counters. So you can watch one of these files and also make sure that all the accesses are going as expected. So watch the actual log. All this code will be open sourced as the cudf stuff lands, and we have an end-to-end thing. So I just wanted to share that because this stuff can be tricky. So I'm going to do a quick time check here. So with that, I guess we're about at time. I do want to kind of, if you want to kind of go deeper, I do want to share a few things. So one is, if you do want to play with the kind of GPU visuals and things like that, you can do that for free at Graphistry. So take your favorite CSV export or Excel or whatever, and then kind of go. Likewise, if you want a pre-configured Rapids environment for all this stuff, notebooks and whatnot, you could launch one of our AMIs. There is a Dask Summit Slack, but it's a little hard to get to the join link. So if you go to the Graphistry Slack, it's linked on our website. I'm happy to answer questions there. I will be hanging out on the Dask Summit Slack channel as well. And then finally, for more information on this stuff, if you want Rapids, go to Rapids AI. More video on the GDS stuff we have with the Pavilion team. And then we're going to be putting all the demos and kind of reference implementations up at our different GitHub repos. So that hopefully I was able to change a little bit about what you think is possible and with modern computing, and hopefully this is of help. So, and enjoy the rest of the Dask Summit.